Alright, time for the draftphysics.com, debatephysics.com also, video presentation. Alright, dealing with a description from start to finish, let's just say, beginning to end, something from the elemental to the more emergent properties of the universe. And so just the physics done, my argument would be correctly. Science done correctly, correct interpretation of the evidence and what can be called the facts that we would base our understanding on. And I will argue that conventional physics has it all wrong, and frankly very wrong. And it's really much simpler than they claim. No entanglements, no woo-verses, no multiverses, none of this complicated woo-y stuff happening. It's all really, really simple to understand. It's a simple mechanical function. It's as simple as a stream flowing to the ocean, okay, and as it goes there with a certain simplicity, it creates all kinds of different functions, all kinds of little eddies and splashes, and stuff shoots up in the air, and all kinds of things happen. And all those things happen for very fundamental and elemental reasons that don't have any mystical elements. They're all quite predictable and dependable in terms of following very strict laws that are entirely unyielding to any human wish. That something can happen without a cause, or that they can change the rules and force something to happen that they'd prefer to happen, or some other kind of nonsense. Dropped my mouse. Anyway, probably don't need it for this part, so I'll just read a paragraph that I wrote. And so, yes, I have to write the rest of the paragraphs that go into the book. But anyway, there is but one elemental universe, one place on the microscopic scale where all events actually happen. So just one point of view, one place you go, very small, very big. You go to one place and you look there, and that's where you'll see the actual functions of the universe. Everything that happens there, everything that happens anywhere else, happens there first. Okay, the only real universe is the universe of electrons and protons, so that's where you have to zoom in, and being pushed about by elemental bits of force possessing a perpetual motion. So there's two kinds of stuff. There's force, little bits, moving the speed of light, very small, all the same, all moving the same, and except they're all moving in different directions. Different places in space, moving at different vectors. And there's just this matter, elemental matter, electrons and protons, and they will encounter bombardment by this force. And the force can either reflect and take energy away from an electron or proton, or it can stick and give it energy, obviously. Anyway, in free space, the bits of force travel at the speed of light, or what should be more appropriately called the speed of force. So this is one of the obvious, wow, they still haven't figured this out. Regular physics still won't say, look, it's time we did away with this idea of a speed of electromagnetic radiation and just recognize that all, of this stuff that looks like elemental force all moves this elemental speed. Gravity, magnetism, electricity, everything moves at this maximum speed when it's in its most discrete, simplest form, free form. When absorbed by an electron or proton, the momentum of the force bit is shared with the mass of the electron or proton, giving the electron or proton motion and momentum. So simply put, the little bit hits the matter, it is essentially absorbed by it, and now the matter has the momentum of the little bit, and obviously it's got to be shared over a larger mass, so the velocity will decline. And this is the function of the universe, that force trapped by matter moves slower. And there's a huge consequence to force moving slower. It doesn't get where it would have gotten because it's moving slower. And that's what creates a lot of disturbance in the force, and in turn in the matter. Yeah, good enough opening, and then I will draw some of it. Alright, here is an illustration figure of this force. So yes, obviously slow down so you can see it better. Okay, so it's just little bits that are traveling the speed of light. And there's, bazillions and bazillions, an incalculable, insane number of discrete bits of this stuff flying through all of space. So this is what space would look like, empty space, okay, is that it's not empty. There's a whole bunch of this stuff flying through it. And this stuff is the whole electromagnetic spectrum. So little bits at a frequency, that is one bit followed by another bit followed by another bit, could be called a photon. And magnetism and gravity are also made out of this stuff that is going to interact with matter. So the all you need to do to see the bigger picture is to see electrons and protons in this environment. Now the trick is the electrons and protons, because of the function of this force, they end up mostly forming atoms. So you don't see electrons and protons as free pieces in the universe very often. They're usually just transferred between atom and atom, and so they don't do any of this freely flying through the universe stuff very often. Supernova, certain things will create that, but they don't do much traveling. And so you don't see the small bits actually being manipulated by the force. You end up seeing the collection of them. And so you might have noticed that the bits of force have two colors, and that represents the fact that there are essentially two separate universes combined, the electron universe and the proton universe. And the two interact with each other in essentially inverse ways. So electrons behave the opposite of protons when hit with the same force. So in the same force field, a proton will move one way, an electron moves the opposite way, that kind of thing. And all it is based on the collection of this force. That is, the force interacts, and either an electron or proton reflects the force or absorbs the momentum. So it's sort of like resonant frequency or tipping something. You can understand if you're moving with something, you can add energy. If you're hit something while it's moving against you, you're liable to just create a loss of energy in the object and a reflection of the energy. All right, so it's so simple, but it does have this subtle nuance. So we'll explain the subtle nuance, but just emphasize the point that there's little lines on the little dots just to show that they have a vector. And direction doesn't matter, though. They can hit something and change their direction, and there's no loss of energy to change direction in the elemental universe. And so that might become apparent as we proceed. So we will add some protons and electrons and explain the functions in a little more detail. So it's simple, but it's all relative for people, right? So I would argue that the electrons and protons have to have the same spatial dimensions. That is, they have to be the same size, because the forces they produce, the interaction with the force, is equal. So the amount of change the electrons create in the universe is the same as the amount of change created by protons in terms of the electricity and the magnetism. Demonstrate that the north side of the magnet is just as strong as the south side, and vice versa for electricity and charge. But they can have different masses. That is, they can be easier and harder to move. So the argument would be is that protons are heavier, so they're harder to move. More force has to hit a proton to move it then it has to hit an electron, and that's why protons end up in the nucleus, and with some electrons, that is the truth, and and the electrons, the rest of the electrons end up on the outside of the atom, on the crust of it, if you want to say it that way. And so that's what basically happens to the elemental bits. So if you go to the elemental universe and look for electrons and protons, 99.99% of the time, you're going to find them in the form of something that looks kind of like an atom, or looks kind of like hydrogen, which would just be basically a very a dipolar piece of matter where you have a proton and an electron staying together and traveling. All right, so this is to represent the electron, and you can say that that's the minus in electricity or charge, or the north in magnetism, and the proton is the plus and the south and blah blah. And basically they're in a field of force that contains both the electron force and the proton force in what one assumes to be equal amounts, and there's equal numbers of protons and electrons in the universe, and it's that mixture of those two fields, and you end up with this very, very simple behavior. There's only three possibilities. If an object is moving with the force, it collects the force and goes faster, so it collects the momentum of the force. So it was going 10 miles an hour in this direction, and a force bit hits it, then it's going 12 miles an hour in this direction, and the force stays there until a piece of force is opposing it. So if the electron is moving this way and a piece of force is going to hit it opposing its direction, then it reflects the force that was pushing it, one element of it, and it also reflects the force that it hit. So two bits of force fly off in opposite directions, and the electron loses momentum in whatever direction it was moving. And then if a proton force hits an electron, it just goes through and comes out an electron force. And that creates essentially Maxwell's drawing of charge, which is you have two opposite objects excreting a force, okay, that is opposite in its function. Now Maxwell draws a force that's going into protons and coming out of electrons, but it's really electron force coming out of electrons, and that's all they can expel, because any proton force that goes into an electron comes out an electron force, and any electron force that goes into a proton comes out proton force. So protons radiate red. All the reflections and all the transitions end up being red, so it just radiates red, and the electron just radiates blue, or white in this case. And that's all that it can radiate. That's how it looks in the universe. And obviously the blue force is inert to protons. The electron force is inert to protons. The proton force is inert to electrons. That is, it won't move it. It'll just get changed. So that's how you create the absence of pressure between the electrons and protons, causing them to be pushed into each other. And the repulsive force, obviously if two protons are in space, all of the electron force that's coming in from both sides gets converted into proton force between them. So there's a great deal of force hitting them that either reflects or they absorb it and move. So they can't possibly stay in that condition of close to each other, because there would be all this extra force coming in, turning into proton force between them and causing them to fly apart. And so that's why they attract. So we'll do a little bit more about atoms and then say, okay, we'll save the details for later, but just understand this perfectly explains charge, and this also explains magnetism. You can see in some simple way these are essentially magnetic monopoles. They behave as if. So, if you had big objects that could do exactly what protons and electrons do, the behavior is going to be the same as if they were a north side magnet and a south side magnet. They'll function exactly the same. Alright, so this is a working simulation of the rules I just described. And as you can see, the little bits of elemental matter clump together. And by the simple rules that, yes, a red can be next to a green, and then another red, and then another green, and another red. So the idea is that as long as they are next to their opposites, there is a strong likelihood that they'll end up close to each other. And if they can see each other directly, that is, green against green is not going to happen. So if there was to be a second row in this simulation here, this one would have to be red, and this one would have to be green, and this one would have to be red. And this is basically the function. So it's obeying the rules, and they're really simple. And you're starting to create what the elements of what I would argue would be the standard nucleus of an atom. So we'll go to describing that. Alright, so if you do imagine that you have this field of force, okay, surrounding both electrons and protons, and they have this tendency, okay, to be pushed into each other by an absence of pressure. That is, they can't see the force that each other radiates. So again, the electron is radiating a force that the proton can't see, essentially. All right, so when they're acting on each other, they can't see the force they're expelling, the radiation, the heat, however you want to describe that. And so they have a tendency to move towards each other, and again, the mass of the proton can be much heavier, so that's why it ends up in the nucleus, is because it's harder to move. But the basic idea is that every electron is always going to be pushed towards any available proton. So wherever it doesn't see a proton, it means it's seeing a place that's comfortable or good. So every time when it looks at the world, all it sees is there are places where there isn't a hostile force coming at it. So wherever there's a proton, it means there isn't the force coming at it. So let's say you were in a very hot environment, lots of light, and you wanted to get cold and you wanted to get cool, and so you saw the cool spot was the place where there was no stuff coming at you, and that's the place where the protons are. The protons look cold or less less hostile from their perspective, and vice versa for the protons, of course. So they end up being attracted. But the trick is that getting close to each other is complicated because the forces that are flying into them are full of nuance. Cell phone calls, all kinds of explosions in space, all kinds of pieces of noise, and which means there's different amounts of this force, okay, and clumps of it moving through space. So it's not an even field, a perfectly even, like they get hit with two pieces and then they get hit with two pieces and they get hit with two pieces. No, they get hit with 10 pieces from this direction and only one piece from this direction, and then a minute later it's 10 pieces from this direction and one piece from this direction. So they're constantly getting jostled, and it's that motion, you could call it heat, of the environment. Okay, there's tons of this force bits, and it's all got a bunch of changes in its density. Okay, so they're constantly getting jostled when they're in the free universe. And so even though the electron wants to get next to the proton, the fact is it keeps getting moved in other directions. Okay, so they can never get too close to each other because there's so much noise in the environment. The electron gets pushed up and then it starts going over here, and then it has to get reattracted and it starts going over here, and then the proton goes over there, and so they're constantly jostling for position, so to speak, and it's never quiet enough for them just to bang into each other. But once they do, okay, then you have what's called a neutron. And I'd say that this is a contradiction with conventional physics, but it really isn't. They concede that neutrons do decay into a proton and an electron. So a neutron is really just a proton and an electron very close together. Oh dear. Yeah, I knew that was going to happen eventually. So enough of that. And we'll just see how much of a difference there is in these colors. That's close enough of a difference. So the electron and the proton can get very close together if you put them in an environment where there's enough pressure, and they're, it's possible because you've changed the frequency or how much they move. So if their frequency is this way, then they're moving a lot of distance, then they can't get close. But if you change it, make it very hot and very more force, and they're jiggling a lot less, then they can get closer together, you could argue. And so once you have this, it's a little harder to break apart. Once they are together, you have to start rejiggling them apart again. You have to start getting them to oscillate before they'll break apart. So they can survive like 8 minutes or something. I think it's something like that. But whatever. We don't need all those details. But this is the fundamental arrangement. And you can understand that if I wanted to get two, let's call these protons. If I want to get two protons close together, the simplest and easiest way to do it would be just to put an electron between them. All right. So you can understand that if I took a neutron, we called this a neutron, and I added a proton, okay, I have this object. And this is basically deuterium. So it's a form of hydrogen, as described. And, this is, you could argue, what holds nucleuses together. And so nucleuses are really just this. I could put, if I put another one, whoops, wrong color. I'll fix that. All right, so the next step in what I would call the evolution of matter would be, you have a proton on either side. Well, you still have 3 dimensions to work with. So there'd be another proton could be over here, another proton could be over here. And then you could imagine a possibility that this electron pulls up a little bit and the other electron pulls down a little bit, or you get this idea that if, like a jack, so I don't know if you remember what jacks are like as a kid, but there's like 4 little things and then, the 2 end points. And so these would be the electrons on the outside, and these would be the 4 protons here. And you could understand that, yes, each electron would be attracted to these protons and repelled by the opposite electron. So the force repelling the electrons keeps them from getting too close to the center of the jack. And but the attraction to the proton keeps them interested. And likewise for the protons, they're both attracted to this electron and attracted to the other electron. So they're in a very stable condition also. And this would basically be helium nucleus. And this is something that can actually travel great distances in space. So this is the first object you could say for certain. I can throw this in space and it will, I can throw it at the moon, for example. I could be on the space shuttle and I could throw helium nucleuses. I can throw them to the moon and they'll get there. If I try to throw protons, they won't get there. Try to throw electrons, they won't get there. But if I throw helium nucleuses, they will get there. And so, I'm not going to go into those details here, but that's all part of the subtleties and nuance of the function. So what I just wish to point out here is that, let me erase. All right, so nucleuses of atoms, I would argue, are basically just additions of deuterium. So you have 1 deuterium, 2 deuteriums, 3 deuteriums, 4 deuteriums, this combination of electron and proton. And the simple fact is, for every electron there's 2 protons. So it's just a matter of arranging, okay, the elements in such a way. It's just unfortunate that's not quite red enough. But anyway, you get the idea. and then the remaining electrons that would balance the number of protons. So some of these you could call neutrons. You know, there's no law against it, but the fact is that once it's arranged, it's the proton on one side of the electron is just as close as the one on the other side. So half of it is a neutron. So if you break it, you can have a neutron fly off, or you can have a proton fly off. There's no way to break it any other way, right? It's 3 elements, so you can only break it where there's 2 elements and 1 element. There's only 2 places to break it, if you get the point. So, and it doesn't matter which way it breaks. It just means that whenever it breaks, so whenever the deuterium is broken, okay, we'll go back to this color. So whenever you take the deuterium, all right, and break it, you can see that, yeah, you either are going to you're either going to separate it here or separate it here. So you're either going to have the 2 element, the neutron going this way, or in this case, the neutron would be going that way. But it doesn't really matter. So you have a proton and a neutron come together. That's a piece of deuterium, and that's a pretty solid piece of matter. And it's elemental. It's what everything else is built out of. So anyway, so back to the nucleus story. So you have this nucleus with the 2-to-1 relationship between the number of protons and electrons. So twice as many protons as electrons. And you could understand from different points of view, it's going to look like proton. And from another point of view, it's going to look like yeah, I did it the wrong way, but it doesn't matter. It's going to look like electron. And so the exterior electrons are just looking for positions. They see a place that looks black, and that's where they want to go. That's conducive to their movement. There's nothing opposing motion towards that. So an electron sees a proton, it's really not seeing anything, and so nothing is repelling it. So that's a place where there's no pressure pushing it against it, and so it wants to head for the proton. And the simple fact is the other electrons are still there, and they provide a counter force. So it wants to go to the proton, but it can't get to the proton because the other electrons are excreting some of that push away force. So it ends up stuck in a position, a distance from the nucleus. So the exterior electrons end up just being in positions where they're where they can hate each other. That is, they can send repulsive force to each other. Okay, and so they keep a distance from each other, but they're attracted to the nucleus, and so they're just stuck in a position at some distance. And you can imagine the further out the electrons go, the more they're getting pushed by the other electrons, blah blah, and the weaker their connection to the nucleus, so the easier they are to kick out. So if you had to push one of these magnets out of its position, the hard ones to push out are in the nucleus. The next hardest are the first row of electrons, and as you go further and further out, they get easier and easier to knock out of place. So instead of the force, the simple, I like the story to be so simple where, yeah, you just have electrons getting hit by force, and that's all there would be. It's just electrons and force, but it's a little nuanced. And so you still have a universe where only the force only interacts with the electrons and protons. But you can understand if the whole thing is a structure that's tied to each other by the force, you can understand that any bit of force that goes in is going to move the whole thing. So now instead of moving an object that had just the mass of an electron, now a piece of force has to move a whole nucleus, or it has to move a whole atom. And so its impetus, its impelling force, its momentum has to be spread over the entire atom in a sense. So something goes in moving the speed of light, comes out going, much, much slower and such. Okay, so I think that's enough of that. All right, just thought I would show a little bit more of the simulation as it's evolved. And you can see that it does tend to make chains, and the chains can eventually fold. And again, it's just creating an inefficiency between them. So over time, they get into very efficient positions where there's a balance of the force between their repulsion to each other and their attraction to the opposite. And as that plays out, they eventually find positions that are harder and harder to break. All right, so let's talk about elasticity or springiness, or the capacity for there to be something called a resident oscillation, or the storage of force. So you have this basic idea that the nucleus of the atom is net positive, very small, very compact, just basically neutrons, just proton, electron, all closely knit together. And yes, there's twice as many protons as electrons in the nucleus. And then you have these electrons on the outside. And the simple argument could be made, I guess I should make these equidistant, is that you can understand that if I pushed on this electron, that is, I hit it with extra electron force, that it would move, momentum would push it in, and in doing that, it's going to end up putting pressure not only on the nucleus, because there's little electrons in the nucleus saying you're getting too close, but it would also put extra pressure on these exterior electrons, so they would tend to push out because they can't really go forward because they don't like this electron. And so in a way, the electron would change its shape, and but in doing so, it's all out of alignment now. It's lost its equilibrium, its balance, and it's going to try to rebalance, essentially. And so either the whole nucleus moves, or something has to readjust so the whole thing goes back to the way it was, which was a steady state, the most probable state, where the forces are equally balanced. And that's what it's going to try to re-achieve. So the idea is that you could push into an atom, and that you can take its shape would just change. You could just understand it as that, just like a rubber ball. It'll deform, okay? And then that's essentially a storage, and then it will go back to its original form. And the idea is that each time an electron moves in this field of force, each time it does this, you can sort of understand that, yes, it would be pushing into the force. And going backwards, there would be fewer reflections, because the force isn't going to hit it as often because it's moving away. And when moving towards, it's going to hit it more often, more reflections. And theoretically, if I could move my hand at the speed that the force moves, you could understand I'll just keep collecting. See, the force would want to reflect here, and then another piece of force would want to reflect here, another piece would reflect here. But the problem is all of those would be going the same speed as my hand forward. So every piece of force I hit as my hand moved, it would all just stick on my hand. And then if I stopped my hand, all of that force would fly off at once. You could understand. Because now it's free to, because it's not stuck to a hand that's moving the same speed. So you can understand that if something is pushing into the field of force, that it would create compressions and expansions in the density of the force. So that's the thing to understand, is the force has a density, okay? And you could have areas where there was an electron that moved, or electrons moved, and it was very dense, and then there's areas where the amount of force is less, and then there's areas where there's a density again. And this is basically how you create photons, electromagnetic signals that you can receive. It's just really where the field of force has been compressed by something moving out, and then relaxed by something moving away. So this would be the part where something moved away, and this would be the part where something moved toward. And these are the signals that we call photon, or electromagnetic radiation. And so they're basically just the oscillations that the matter is doing, because it's elastic. So it's getting hit by the force, and it has to push the force back out. and it's got to achieve an equilibrium with that force. So this is where you can start to understand that I could say something like, all motion is just heat. So every time something moves, it's really just a form of heat, because you're just really taking matter and moving it when there's something that's hot. It's going back and forth. And it doesn't matter that it's going back and forth, it just matters that it's moving. And it's the motion that is the heat, and the energy is in the universe. So you could argue that the universe is full of heat, and everything has to find an equilibrium with that temperature. Anything that's colder than the universe has to get as hot as the universe. You could understand anything hotter than the universe will end up radiating that extra heat, that extra motion. It'll push out more than the universe is pushing in, if you get the drift. So the amount of heat could be just represented by a jiggling line, and you can understand that if the universe is this, if this is if this is Einstein's E equals mc squared, and what that's really saying is that the amount of heat in any piece of the universe, any section, any sphere of space. So I could take a sphere of empty space, and the average sphere of empty space has a certain amount of force moving in it, has a certain amount of potential motion. And what can happen as matter interacts is the matter can actually have less or more heat in it, okay, than the average of the universe. And so in the heat, the motion always moves from things moving a lot to things moving a little. Things moving a little can't give energy to things moving a lot. The energy can only move from things moving a lot to things moving little. You can't pour desert into water. You can only pour water into a desert. I think that'll work as an analogy. So I drew this for a reason. I have to think what the reason was. I'll get back to you. All right, so the simple argument is so I have a piece of complex matter, and lots of atoms, lots of stuff going on. So there's lots of different motions. There's the motion of the stuff in the nucleus. There's the motion of the electrons around the atoms. And then there's the motion of the atoms themselves jiggling about. And so it has a certain amount of average motion. And if the universe's average motion is less than that, then it gets to be like a sun or something, and it's going to radiate, okay, that extra. And if it's less than, by some phenomenon that I am unaware of, then it's going to end up getting hotter. So in a sense, you know that every piece of matter, large piece of matter, can never get to an absolute cold temperature, because the universe is never at an absolute cold temperature. You can't escape the elemental force that's actually holding the atom together. So if you could achieve something called an absolute cold, that is no force hitting it, and it would just radiate whatever energy it has, the atom would just fly apart. Because there'd be nothing to push it together. So that's part of the understanding of the push-averse part, that a push, okay, is elemental. Something hitting something and giving it momentum, and there's really no opposite function. There's no such thing as a pull. You can only bang into something and push it. You can't just magically say, move here. So everything that looks like a pull is just in some way or other an inverted push. A really simple concept that physics really should be completely on board with as a concept, because it's so obvious that's the way the universe works. That pulls can't be drawn. I can't draw a pull. I mean, there's no way for me to draw you a pull, right? I have this object over here and it says pull. I can't draw you what pull would be, but I can clearly draw you push. Easy. Something banged into it, made it move. That you can understand. And you can certainly understand, as I've already explained, that all I have to do is block the force that would have hit this. And if I block the force that would have hit this, well, that's the same thing as a pull. I've just taken away the push. So in a sense, that's gravity, and that's probably the next thing to talk about. It's just the simple principle that if something blocks the force coming from this direction, then there can't be any force hitting this object, and there can't be any force hitting this object, and obviously they're just pushed together. And that concept happens regardless of charge. So even if I didn't explain to you how the electron force and the proton force are two different forces, but they are structurally the same. They just have the nuance of being acting one way, of an electron seeing the same force differently than the proton sees it. But even if I had a vessel just full of little BBs in a box, and the BBs bounced off the side and they never lost their velocity, and I put two objects in there, the two objects will be pushed together because they will in fact shadow each other from the BBs. More BBs will hit them on the faces that are facing away from each other than the faces where they're facing each other. And just a statistical fact. So they'll end up moving towards each other. All right, enough of that. All right, so if I threw just electrons and protons into a universe of just force with no other matter in it, the idea would be is that it would quickly start making hydrogen atoms, just a proton with an electron. I mean, they say a proton by itself is hydrogen, also a form of hydrogen, which I think is a stretch. But anyway, and then tritium would be the easy one. I mean, deuterium. So the proton, electron, proton kind of idea. Where you have a neutron and an extra proton, that would be what the universe is going to do, is consolidate the matter. Now, left to their own devices, okay, they're going to need something else to make all the rest of the atoms. The heavier atoms require more pressure and heat, so to speak, more compressing energy than just a bunch of electrons and protons pushing on each other. They need to compress, have extra force. And so they have to be, the heavier elements have to be created inside some pressurized vessel. And the argument would be is that's what gravity creates. So once you have a bunch of atoms in the universe, then you can understand the atoms will consolidate into clumps of compounds and elements and just blobs of stuff, clumps of elemental matter. And it'll keep clumping. That's the tendency. So we know our solar system used to have a whole bunch of crap in it, and that it all got caught. It all got consolidated into bigger and bigger clumps. Okay, and so the universe by itself clumps. All right, but there's mechanisms that there's nuance to how exactly it does that. There's rules. So I'm just going to talk about, once you understand the idea that you are clumping the universe, that has a consequence related to the fact that I use this idea of heat, and that heat is the engine of the universe motion. All right. So once you have this stuff clumping, okay, you can understand that it itself now, okay, is collecting energy. And, energy has to go through the matter. And so the force, when it goes through a lot of matter, you can understand that it's going to hit a lot of electrons and protons. So it's going to spend a lot of time, okay, moving an electron or a proton. So as the force bangs into the matter, all right, it's going to keep its momentum, is going to keep its direction, all right. It's going to keep that motion. And so from every side, it's pushing towards this center, okay. And the trick is that it's doing that pushing, all right. You can understand because of the simple fact that when the force is free, it's going the speed of light. Might as well get rid of that. You don't need this for the moment. Where is it? That's the one I want. There it is. Don't need that. Okay. So, you can understand that at the speed of light, it would travel a certain distance in a certain amount of time. But when it's pushing an electron, for example, say there's a few bits of force pushing the electron, it's going to be going much slower. So it's only going to go that far in the same amount of time. So it's being delayed in its progress through the universe. The force is being delayed in getting to where it would have been if it was in free space. So pushing matter has a consequence, and that's happening inside of all these material objects in space, like the Earth and the Moon and the Sun. What's happening is that force goes in, and it takes it a very long time, by its standards, compared to the speed of light, to get back out of the Earth, because it has to push matter it keeps hitting matter, and therefore by hitting matter, because it's a high density of electrons and protons, it keeps being slowed down, essentially, and getting to the point where that electron pushes on the exterior universe and compresses it, and gives the force back, essentially. Hits a counter force that absorbs its energy, okay, and stops it from moving out. All right? So as the electron moves out, it's getting hit with more force, which stops it from moving out, and then eventually it moves back in. All right, so it's oscillating constantly. Everything's oscillating, and the universe is basically at equilibrium. You can understand with all of these objects have to be at equilibrium, because they're sitting there for billions of years, and they're basically taking in as much stuff as they're excreting, because they're not getting bigger and bigger. Now, materially, they're getting bigger and bigger, especially in the early solar system. They got a lot bigger, but they're not getting bigger anymore. And so now they have to be at an equilibrium with the universe. And the equilibrium is demonstrated. You can see how hot the universe really is by recognizing that the Earth has a bunch of very hot material inside of it. So it's molten in the center, and it's mostly liquid, or I don't know what you call a semi-liquid state. Very hot, and it's might be 4,000 degrees centigrade, I believe is the number, in the center. And obviously, as you allow that heat to radiate out, it's going over a bigger and bigger density of the Earth, so it's going to get colder and colder because it's heating more and more material. So the same energy is being spread over a huge amount of mass, and so by the time it gets to the surface, it maybe is only a few hundred degrees Kelvin, which would be some sort of minus degrees in centigrade, but it's real degrees, it's real heat, it's real motion it still has. And that real motion is higher than the motion in the universe, so it excretes it to the universe, gives it back essentially as a density in the force. So the real point is, I don't know how to, I guess I could just redraw it, is to understand that there's a bunch more energy in the Earth than the average density of empty space. So again, if I took that sphere of empty space and counted how many bits of force are in it, what's inside of the Earth per the same size sphere, I'm just going to draw it bigger to make it easier to see, there's a lot more in it, because there's a whole bunch of force moving slower. So you can understand it's collected the same amount as that in this little tiny bit of distance. And then there's another layer, another layer, another layer. So each layer of the Earth, okay, has a bunch of force that's equal to the same amount that would have been here. So you could say it's this has 15 bits of force in it, then this number could be 5,000 by comparison. Because of how slow the force is moving, it's collected a whole bunch of extra force. There's a huge density of force. It's all catching up to each other, so to speak. Because I slowed the first one down, I slowed some more down, I'm concentrating how much force is in a given amount of space because I've slowed it down. So I'm concentrating it. So the Earth is a sink for force. It's collecting it. Okay, so every time one of these gravitational bodies gets hot, it essentially makes the universe colder because it's sinking force. So for every force bit that gets stuck moving slower in the Earth, it's a force bit that's not in space. It's not free where it would have been. So you can just kind of understand as you have more matter collecting more heat, you end up with less force on the external universe, which means less pressure. So that's the equalizing factor that the universe is caught in, is that for every consolidation of matter, every galaxy that forms, everything that consolidates the matter and slows the force down by moving the matter towards each other, is essentially slowing the force down, using it. And for every bit of force being occupied pushing matter, it means it's not a piece of force free in the universe. And so essentially the two things are in an equilibrium. If you start to compress too much matter, then there's too little force to continue compressing, and it expands again. So the whole universe is expanding and contracting based on how much force, has been used pushing matter into these small spaces. And every time something supernovas, then a whole bunch of energy goes back into the universe as free force, and a bunch of matter now has to be pushed back into being consolidated. So it's heated the universe. So it's really just a heat engine, and this sort of just completely defeats what is called bent space-time, because you really can't blame gravity on a non-existent non-force. It's clearly a force, and it's clearly creating real energy in the universe. The heat inside the Earth is real energy. Okay, it can't be considered something else. Heat. Yeah. And so it's it's real motion. And so you can't sit there and say, well, I have a non-force that created real momentum, real heat, real motion in objects. That's free energy. So the only explanation that can possibly make any sense is you have to understand that it's a real force, and that the real force excretes back out of the Earth and merely compresses other objects and makes them hot. Okay, so this object heats the Earth, this other object gets heated by the Earth. So that's the balance in the force, that's the balance in the universe. So you could argue, I really probably don't have to make that argument, that anything going this way, there's some place in the universe where something's going that way, that it all balances out. And it's the same for the heat in the universe, that there's the rest of the universe is compressing the Earth, and the Earth is adding its contribution to compressing everything else in the universe. We're all adding to each other's, the force compressing us, by merely being in equilibrium and consuming the force, by having it occupied in this little tiny area pushing matter. All right. So this is, it's a pretty important fact that, physicists don't acknowledge the fact that our mass creates a constant pressure inside the Earth, that we're constantly pushing momentum-wise into the Earth. So I have pointed out that you could take a scale, a regular weigh somebody scale, and you could push something into it and see what velocity you need to make the scale read the person's weight. Okay, so I could take an elephant and move it at 1 mile an hour, and it'll weigh elephant. I could take a mouse and move it 1 mile an hour, and it will weigh mouse. So constantly, as we're sitting on the Earth, we're pressurizing, we're pushing momentum into the Earth. And so it's real energy that gravity causes. It's real heat, it causes. It's real motion, it causes. And the motion has to somehow be causing the gravity. It has to somehow cycle. And it can't be a bent geodesic. And the universe would just keep getting hotter and hotter if you could make all of this heat for free, that the Earth is actually really radiating. If it was free, then the universe would just get hotter and hotter and hotter and hotter. So obviously that heat gets consumed compressing other objects in space. It gets absorbed. So this is the absorption cycle, I guess you could call it. All right, so that's probably enough for this first volume, all right, to get just some basic mechanics down. And the rest of it's just about the simple truth that it's just momentum transfers, and that's all there is in the universe. The force has momentum, gives its momentum to matter. When it gives its momentum to matter, it essentially is degraded as a force. The other interesting fact is if, let's say I had an electron and I did make it, I kept collecting more and more force in a direction. So that is, I sent a bunch of high energy photons, that is high density, small frequency radiation. Okay, so it's very compact. And I sent a stream of that, and so it hits the electron, and the electron collects quite a few bits. Well, let's just say for each bit it goes 10% of the speed of light, and so you're saying whatever, 10% of 90%, and then 10% of 80%, and then 10% of 70. So it could end up going almost the speed of light. Well, if it was going almost the speed of light, then this force bits have all regained their original speed, and now they aren't in deficit, which is an interesting fact, that the slower the electron moves, the more it has degraded the force. That is, the more it's consumed its energy, so to speak. And the faster the electron's going, the less it's consumed the energy of the force, because the force is back to almost moving the speed of light. So, just an interesting little thing to throw in. I find it interesting. So the rest of it is just talking about how these exchanges of momentum take place, how momentum is always conserved, that it's always just about a mass moving a velocity, and so you can take a big mass and bang it on the ground, and now the ground has a bunch of little masses moving with velocity, and it always adds up. Any extra motion the ground gets, any extra heat it collects, will be completely proportional to the amount of energy you took out of the big thing moving. So the less the big thing's moving, the more you've changed its motion, all of that change will be somewhere else, and it can all be followed. And so that's the simple law of conservation, that's conservation of motion. Newton had it right, and there really isn't anything called kinetic energy or 1/2 mv squared. There's just mv, and that's the only thing the universe is concerned with, is a mass moving, and the force is a mass moving. Yeah, so we'll just get into the fact that you can change the frequency, we get more into the charge stuff, but I mean, all the elemental bits I've just given you, there's energy is just motion, force is just motion, weight is just motion, pressure is just motion, heat is just motion. It's all the same thing, and it just has to do with masses moving, and that's it. There's no other concept running the universe. There's just momentum. Momentum in the force, momentum in matter. That's it. The matter has no innate motion. The force is nothing but motion. And it's just understanding there's just, if you know what Sisyphus is, there's just Sisyphuses, the force, and boulders. And a Sisyphus can have the day off and just be running very fast and going wherever he wants, or the Sisyphus can be stuck pushing a boulder. And those are the two states the universe can be in. Force freely flying, or force pushing an electron or proton. And that's it for the elemental mechanical functions. There really aren't any others. That's it. It's just force pushing matter. And then when matter moves, it changes where force goes. It pushes on the force. All right. So we'll call that a video. Number 1 and such. And so forth. And whatnot.